introduction. So my name is Nir Lotan. I'm a deep learning product manager from Advanced Analytics at Intel. Advanced Analytics is a team that we specialize in machine learning. Generally, a lot of work internally within Intel using machine learning to make processes more efficient. And also we have some external products in the health domain and also in deep learning. How many of you have practiced deep learning? Just so I would know. Okay, that's a nice number. How many have heard about deep learning? Okay, so it's a little bit more. I will try to be very concise about the introduction of deep learning, assuming you know. And maybe we'll have either save some time or have some time for a demo. Basically, as you know, deep learning is not just a promising word. It's definitely one of the most innovative areas in machine learning in the last years. It's not new, but thanks to the growing compute power, we are able to achieve more tasks and get better results with deep learning. So deep learning excels mainly on cognitive tasks. So we're talking about mainly visual understanding, analyzing pictures and videos, natural language processing with regards to the text itself, and also speech recognition, additional tasks as well. But these are the main tasks that we hear about in the industry that are practicing deep learning. And very briefly, the process itself has two main steps. The training phase. So deep learning is a supervised type of machine learning. We provide lots of labeled input. We create the neural network. I have another slide about that. We train the model. Once we have a trained model, we complete the training phase. And then the second step is the inference part. So we use this trained model in different applications. So again, the training part usually is done in the data center. It takes hours, days, sometimes even weeks. And we're using extensive compute power. Here in this example, we provide lots of labeled images for the different images tasks. Once you have a trained model, in the inference part, you use it usually at the endpoint. It could be a data center, but it could be a small device like a virtual headset. It could be in a car. It could be in a mobile phone. And here the idea is to have the results as fast as we can. Again, I'll do this very briefly because I'm assuming most of you know it. The deep learning model itself is inspired by the human brain. We have the depth of the model that is defined by the number of hidden layers. There is the topology, which is the structure of the model and the connections between them. The different neurons have the different mathematical functions. And the output layer, in the training phase, we will compare the output of every training interval with the actual truth and back propagate and update in an iterative process the model in the training part until we get a good representation of the truth. And in the inference part, the output layer will provide us the probability of each of the categories of being what it is. So again, as part of our work, I will review some of the use cases we did with deep learning, but we also, in order to make deep learning easier, and we want more people to practice deep learning, we want more people to do it on Intel hardware. So we created a training tool, a deep learning training tool. So some of these examples I will share how we did it with this tool, but basically it's a tool that is designed on top of open source, known open source deep learning frameworks. Currently we work on top of Caffe and TensorFlow. The idea is to allow data scientists, researchers, developers to easily get results with deep learning, so it has some productivity tools, but also to set up the environment easily. And another key aspect here is that it's not necessarily the open source framework as it is, but it's extensively optimized. So basically you get better performance. It can be 10x or even 100x faster in the training phase comparing to taking out the open source, running it on a regular CPU. So here are some of the use cases we ran with the tool, and I'll mention them in this short talk. We're working with a lot of automotive companies who are working on autonomous cars. And I think that's one of the most common use case for deep learning, doing object detection, image classification, semantic segmentation, all images of the autonomous cars. We had a project with a company doing automatic product recognition of a shopping cart. So you walk around the supermarket, you drop a product into your shopping cart, and Intel RealSense camera take a snapshot of that product, and you classify the product, and when you want to go out, you have your account already ready for you. There is another product, the Intel virtual headset. So this is a product you can go outside and buy in the market, and basically you interact with the headset using hand gestures. No keyboard, no, it's voice and hand gestures. So basically we had to run classifiers of hand gestures, first identifying what is a hand and what is just an object, and then the different gestures. So that we use deep learning for that as well. There is a Kaggle competition that Intel is sponsoring for screening cervical cancer. This is a competition that's still on. You can still join it. So we recommend deep learning, running deep learning there, and we already started, and we see some nice results with deep learning. And again, the nice thing is you don't need to define any features. You just train the model. And another use case from the text domain is there is a joint project of Intel, Vox Media, and a foundation that was funded by Lady Gaga. That the target of this project is to identify sexual harassments on the internet. So in Twitter, in online forums, we try to identify sexual harassment and provide to the community a tool to classify different tweets and forum discussions if they're harassing or not. And that's another iterative project that we do. Currently, we actually use traditional machine learning, and we're trying to achieve better results with deep learning. So the process of deep learning, again, I'll try to be very brief and maybe just talk about the examples that we did, is the data preparation. After you have the data, you build a model, you do the training. This could be an iterative process, and also there is the part of model deployment and inference, which has its own challenges. So, and I'll talk a little bit about each step. So the data preparation, I think everyone knows getting the data is hard. In the industry, it's also harder because a lot of the free data out there is only allowed for non-commercial use. So a lot of companies have a lot of issues around getting the data. Once you have the data, labeling the data, which is today commonly done by people, if it's image classification, it's easier. Text classification is easier, but object detection or image segmentation is much harder task. And there are a lot of tools just to do this. Once you have your data, you need to normalize it. Either if it's images or text, making sure all the characters, the valid characters are there. For images, that's the same size, number of channels. And also, another problem that we had is a lot of time you have data, but it's unbalanced. So for some categories, you have a lot of samples, and for other categories, you don't have as many samples. And then there are ways to do data augmentation. So for example, for images, you can rotate images, you can zoom in, zoom out, and it still will, although it's the same image, it will still significantly improve your data. So this is how we're doing it with our tool, and basically you can see we're doing it for text, for images, quite commonly. So the next step is building a model. First you need to select the framework. Usually data scientists have their preferred framework, but actually depending on the task you may want to choose different frameworks. So for example, some frameworks are better in inference runtime. Other frameworks are easier to use to build the models. So that's the first step, is selecting. We want to use Caffe, TensorFlow, Theano, MXNet, which is good for distributed tasks. So each framework has its advantages. Second step is to select or create your own or customize the network topology. Different topologies are good for different tasks. and also for different data sets. So that's the second step that you do when you build the model. You select your model. Usually you would start with an out-of-the-box or commonly known topology, and then you will customize it. The next step is to define hyperparameters, how many epochs or iterations you want to run, how many images per batch. This significantly influences also the training time, but also the accuracy, and also what is the solver type. So these are really high level. There are a lot of considerations to take here. Again, I put some screens from our application. You define the layer, you select the layer, you can see the topology. But it's a common task. Next, throughout the model training can take, for some, if you take ImageNet, for example, it can take sometimes even weeks. Mostly it will take hours or maybe days. So during the model training, usually you want to see the progress, you want to see if your model is converging, if the loss is going down. But that's not even always accurate for one of the models. It ran for 2 weeks. There was no convergence, but in the last day, you suddenly see it significantly getting a lower loss. So that's something really tricky. How do you manage your compute resources to be efficient if you want to run many training tasks and many different parameters? This is how it's done in our tool. Again, some visualizations to show you the progress, the remaining time. So in the inference part, there are a lot of other considerations. Now it really depends on where do I want to deploy my model. So first I will need to convert it. Usually the model is written in a framework language, and I would want to run it in a runtime environment. Maybe you need to translate it from Python to C. Maybe you need to, there are a lot of open source libraries. You can use OpenVX, OpenCL, but they're different from the libraries used in the training part. You may want to compress it. So sometimes you have a model with really good accuracy, but from memory perspective, it will not fit into your device, edge device. So there are a lot of tools and methodologies to compress the model, sometimes to quantize the layers, to prune some of them don't really contribute that much to the accuracy, and maybe you will compromise on the accuracy. Okay, convert it to the different time, and eventually you want to infer it in real time. And as I said, there is an experimentation process both in the training part and also in the whole process of training and inference. So you will change the hyperparameters, you will try different topologies, changing the layers, changing the solver types, and comparing results. And these are some of the parameters you can play with. And eventually, this is the process of doing the deep learning. In parallel to all these tasks, there are a lot of additional considerations you want to take. So some of it is, there are a lot of algorithmic features that can help you with this work. One is hyperparameter optimizations. There is a lot of research being done on which hyperparameters would generally give you the best results. So you can start off not with a random number, but with something that is optimized. But you need to take into consideration that it also has to be optimized to your hardware. And also, we did some research on doing hyperparameters optimization, not only with regards to the accuracy, but also with the runtime. So you can optimize it to have the same results with shorter training time. Another thing that we did is transfer learning. It's also available in the tool. So basically, you can take a pre-trained model that was trained on ImageNet, which is a large data set, and use the model, and maybe just fine-tuning is, for example, fixing some of the layers and saying, I will just change the last layer. Or I will change mainly the last layer and give a factor to the training process of the previous layers. Transfer learning and fine-tuning will give you faster results, and usually for some cases you will get better results depending on your data set. If it's smaller, but not too small, so you don't cause overfitting, so you would use transfer learning. And again, as I said, we use extensive optimizations and compressions if you want to have the model in the virtual headset, for example, that I showed you before. Then this requires, it has a low memory footprint, you need to compress the model, So we had to compromise on accuracy, but you try to do it in a smart way. Another thing is, from performance perspective, is the ability to get the results faster. So another way is, one way is optimization of the code. So as I said, we provide the framework that is optimized to run on a CPU. So basically you can get faster results, but you can also use multiple servers. So if you work, for example, in a university that already had a data center, we created an easy-to-use Python API, and basically we're using distributed machines. So for example, for one of the training tasks, we took 4 servers, and using these four servers, we didn't get 4 times faster the results, but 3.6 times faster. So combining with the software optimizations, this is significant. And here we're, by the way, as a side note, we're using a lot of open source technologies or frameworks. We're using Docker and Kubernetes, which is commonly used in the industry. Another point is a lot of visualizations help you throughout the process. So sometimes you can visualize the different layers and see their contribution to the classification. You can use some confusion matrix, so numeric visualizations of seeing exactly where the problems are. And obviously for other tasks like object detection, image segmentation, you can actually see the results yourself. And eventually, I think if you try out our tool and download it, hopefully, at the end you'll see you can do a lot of experiments very quickly with it. But eventually, if you want to get the best results, you cannot avoid, but you have to customize your own code. So it's either customizing the network or the layers, but eventually you will have to go in, deep dive and write code. And we also have, in our tool, we are aware of it, so we're providing Jupyter notebook interface, so you can use and write your own Python code, and we have a lot of examples there for the different tasks that I spoke, so you can actually see the code of the task that I showed you before. So basically, this is marketing stuff. I would really like you to download the tool and try it. Our vision is to have, to help developers drive deep learning adoption. Okay, so basically, we're providing a very easy to use installer. You have a GUI installer to install your deep learning frameworks on your server or locally on your computer if it's a Linux machine or a Mac. And it will give you all the optimized frameworks, all the examples that I told you before. We are working and committed to improve the performance in one of our next versions. I don't know if it will be the next one or the one after that. You will get 100 times faster results with TensorFlow using the tool. So we will contribute this code also to the community, and it will be part of the TensorFlow code. But basically the idea is that you will get it significantly easier. We created this, and it's all open sourced API for running distributed code, both for Caffe and TensorFlow, including cluster management, so setting up your clusters and doing the training itself. And we're also trying to bring a lot of productivity tools to make the experimentation part significantly faster. So I was asked this to finish on time, so 1 minute for questions. And I'd be happy to demo the tool outside if you want, or you can Google it and find it and download it, use it. Thank you.
Any questions?
Hello. Hi. How do you compare your speed improvement to GPU? Because that's, I guess, your main competitor when going to deep learning training.
So it's a good question. It really depends on the task. I can show you really nice numbers how we beat GPUs, but that would be in specific tasks. For different tasks, GPU would do better. I guess every person has to check it for their own. I think the promise that we give here is that without purchasing GPU, you will get significantly faster results. So even if you have GPU already today, you can download this and try to get additional. So you basically get additional hardware resources that you already have. I can run this tool on my laptop here. So again, it will not be comparing to any server, but it will be significantly faster than downloading the open source. And also, if someone is starting with deep learning, before they run and purchase GPU, they can start off getting a better starting point. Additionally, Intel is working on the accelerator, and there is a rich roadmap of hardware accelerators that if you want the best results, you will get even better results with these accelerators. You need to turn it on and wait for 10 seconds, right?
Hello?
Yes.
Just for clarification, is it optimized for the inner chip Intel GPU?
Yes. No, sorry. Not Intel GPU, actually the CPU itself. It's not Intel has the Iris component. It's not using that. It's using extensive hardware optimization for running the convolutional network on the CPU itself. So if you're running on a Xeon machine, which is a server, it doesn't have the graphic card there.
Okay, so it doesn't use like QuickSync, which uses the internal CPU architecture for acceleration.
I'm not sure about QuickSync. I have to check that.
Does it support laptops or only servers?
Yes, we recommend i7 and Core i7, but practically yes.
Okay, I'm sorry that we don't have time for further questions. We have to move on. So let's thank the speaker again.
Thank you.